New pictures captured by the James Webb Space Telescope have staggered specialists. Rather than merely expanding our understanding of the universe, these photographs have uncovered an unsettling reality. Our perpetual consciousness is insufficient to comprehend the possible implications of the universe's earliest stages. The theory of the Big Bang appears to be reaching its limits, leading us to consider new hypotheses about the origins of the universe. The question arises, how was the universe formed? And why does this new revelation challenge even the most experienced specialists to decipher more about the Big Bang and the intricate details of these discoveries? What if we examine the possibility that the Big Bang itself defies standard reasoning? Perhaps the Big Bang was not an explosion in pre-existing space. Instead, it might have been space itself that began approximately 13.8 billion years ago, alongside matter and time. In physics and cosmology, singularities describe points where gravity becomes so intense that the curvature of space-time becomes infinite. Today, billions of years after the universe's inception, we see that our immense home is part of a grand cycle. For scientists, this represents a fundamental aspect of the universe, as its very existence suggests an infinite evolution. However, it's crucial to understand that the universe is not expanding into pre-existing space. Rather, space itself is continuously stretching. According to current theories, the first stars began to shine around 200 to 300 million years after the Big Bang, marking the end of the so-called Dark Ages. This was the period when the first luminous celestial objects merged to form mature systems. However, how rapidly these vast systems formed remains a perplexing mystery. A wealth of information emerged with the first images captured by the James Webb Space Telescope in July 2022. Scientists revealed that the telescope had detected unique cosmic systems, some of which existed around 300 million years after the universe's formation. Unlike the massive, long-lasting structures that formed much later, these early galaxies were significantly smaller and less massive, aligning well with the scientific model accepted by researchers. The density of matter in the early universe was simply not sufficient to create galaxies as large as those observed today. What began as the identification of 6 glowing, red-shifted spots from the telescope concluded with the unveiling of one of the most significant cosmic mysteries in recent years. Although these newly discovered galaxies are similar in age to more recently recorded ones, they are nearly as expansive as our own Milky Way. This has created an intriguing mystery. After analyzing a series of images captured by the telescope's near-infrared camera, researchers identified the light sources. Using redshift, they confirmed that the light from these objects took over 1 billion years to reach our eyes on Earth. As a result, we are observing structures that existed around 570 million years after the Big Bang. By studying the characteristics of these systems, it was concluded that the telescope captured 6 early galaxies in the images. Astonishingly, these galaxies were so massive that they challenged conventional cosmological theories. Instead of the expected smaller galactic structures, scientists identified galaxies nearly as large as the Milky Way, despite forming early in the universe's history. If we continue analyzing the data gathered by the James Webb Telescope, these gravitationally bound clusters of stars were already more than 10 billion times the mass of the Sun at the time, with one potentially exceeding 10 billion solar masses. Whether this scenario is accepted, the mystery remains unresolved. For instance, there must have been significantly more baryonic mass in the early universe than previously predicted, which poses a problem. The objects identified challenge nearly all standard cosmological theories. If even one of these vast systems proves to be real, it would upend our prior assumptions. Furthermore, the density of matter in the early universe would need to be several times higher than previously estimated to explain this phenomenon. Another peculiar explanation hinges on how these cosmic systems formed, a process that remains entirely unknown. These discoveries and the debates surrounding the Big Bang have prompted some researchers to diverge from the theory. Various astrophysicists with alternative viewpoints feel their perspectives are not being adequately heard in scientific journals. Even those who express doubts about existing theories are often labeled as irrational. Yet, clearly, even proponents of the Big Bang theory are continually confronted with unresolved questions requiring convincing answers. These questions include specific issues such as, why and how did something emerge from nothing 13.8 billion years ago? Can something truly arise from nothing? Was there a triggering event, or was it all a coincidence? Steven Weinberg noted that the concept of time, as we understand it, began with the Big Bang itself. Thus, the process could not have been triggered by something external to it. A similarly perplexing question relates to the uniformity of radiation and matter density throughout the universe. Regardless of the direction or distance we observe, we find similar densities and distributions of galaxies, nebulae, and radiation. Conventional models explain this anomaly through the theory of cosmic inflation. However, some experts extend this assumption with a theory of eternal inflation. According to this idea, inflation has only ceased in certain regions, like bubbles, while continuing endlessly elsewhere. This suggests that multiple universes could be forming within these bubbles, each with its own unique physical laws. Within this framework, a fundamental question arises. What if our universe does not represent the entire picture? More intriguingly, what if another universe existed before our own? In this case, the Big Bang becomes part of a larger cycle. According to this view, our universe is part of a greater multiverse, within which an eternal cycle of decay and renewal of universes occurs. However, this is not the only perspective in cosmology. In 1955, for instance, an article suggested there could never have been a Big Bang, proposing instead that the universe has existed eternally. Exploring quantum physics and string theory also raises fascinating possibilities. Some experiments suggest that our universe, and everything within it, could merely be a flat, three-dimensional projection on a higher dimensional surface. This implies that our reality might be the result of a higher-level simulation. While this may seem like the plot of a science fiction film, it could connect to the Kardashev scale, which measures a civilization's level of advancement based on its ability to harness energy. A Type 3 civilization, capable of utilizing the energy of an entire universe, might have created such a simulation. These profound questions lie at the heart of cosmology. The new images from the James Webb Space Telescope have reignited discussions about the true nature of our universe, challenging established theories and prompting scientists to reconsider key aspects of cosmological understanding. At the heart of these discussions lies a simple but profound realization. Our understanding of the universe is still in its infancy. The discoveries from the James Webb Space Telescope underscore the need for new models and perspectives in cosmology. As scientists grapple with these revelations, they are forced to confront questions that go beyond physics and delve into the philosophical nature of existence itself. For example, if the universe emerged from a singularity, what mechanisms governed that event? Could the laws of physics, as we know them, even apply in such extreme conditions? And if not, what alternative frameworks might explain the phenomenon? These questions point to the limits of current scientific models and the necessity of developing new paradigms to explain the early universe. One possible avenue of exploration lies in quantum gravity, a theoretical framework that seeks to unify quantum mechanics and general relativity. Quantum gravity could potentially illuminate the nature of space-time during the earliest moments of the Big Bang. Similarly, advancements in string theory might help us understand how fundamental forces interacted in the extreme conditions of the early universe. Another fascinating avenue is the study of dark matter and dark energy, which together comprise over 95% of the universe's total mass energy content. These mysterious substances may hold the key to understanding how galaxies formed and evolved in the aftermath of the Big Bang. Observations from the James Webb Space Telescope could provide critical data to refine our models of dark matter and energy. The possibility of a multiverse also raises questions about our place in the cosmos. If our universe is just one of many, how do these universes interact? Could the formation of one universe influence the properties of another? And what does this mean for our understanding of life and consciousness? These are questions that stretch the boundaries of human imagination and scientific inquiry. Despite these mysteries, The discoveries of the James Webb Space Telescope mark a significant step forward in our quest to understand the universe. By peering into the distant past, this remarkable instrument has given us a glimpse of the cosmos as it existed billions of years ago, offering clues to its origins and evolution. As scientists continue to analyze the telescope's data, they are likely to uncover even more surprises that challenge our assumptions and expand our knowledge. The journey of discovery is far from over, and each new revelation brings us closer to answering the fundamental questions about the nature of reality, the origins of the universe, and our place within it. Suppositions about how rapidly frameworks framed in the universe's earliest stages. These frameworks, distinguished within a few 100 million years of the Big Bang, appear exceptionally developed and gigantic, in defiance of assumptions based on current cosmological models. One of the unavoidable issues raised by these discoveries is the nature of inflation, as proposed by the predominant hypothesis. Inflation occurred within fractions of a second after the enormous detonation, making the universe expand rapidly and decisively. This rapid expansion would explain the consistency of the cosmic microwave background radiation observed across the universe today. However, the new findings suggest complexities in the early development of the universe that may require corrections to inflationary models. The development of galaxies like those seen by the Webb telescope pushes cosmologists to rethink the conditions and processes governing the universe's initial development. These gigantic frameworks, now vast in size and mass, suggest a matter density that surpasses previous estimates. The mystery continues as scientists consider how such massive structures might have formed and evolved in such a relatively short cosmological timeframe. Moreover, the discovery of these early frameworks raises intriguing questions about the nature of dark matter and dark energy, two elusive components that make up the majority of the universe's mass and energy content. While dark matter is understood to provide the gravitational foundation for galaxy formation, the distribution and properties of dark matter in the early universe remain uncertain. In line with these astrophysical mysteries, theoretical physicists are exploring alternative cosmological models that challenge the standard Big Bang perspective. Some theories suggest that our universe is just one among many in a vast multiverse, each with its own distinct physical laws and constants. These ideas, emerging from advancements in string theory and quantum cosmology, suggest a more complex and interconnected universe than previously imagined. One idea gaining traction is the concept of eternal inflation, in which universes continually emerge from a larger expanding space. This theory proposes that our universe may be just one bubble among countless others, each with its own unique properties. The challenge lies in finding observational evidence to support such speculative ideas, as they stretch the limits of empirical verification. Another provocative hypothesis is that our universe exists within a simulated reality, similar to a computer-generated game. This idea draws parallels to advancements in artificial intelligence and computational science, where simulations can replicate complex systems with surprising accuracy. If true, our perception of reality as a singular physical universe could be fundamentally altered, raising profound philosophical and scientific questions about the nature of existence. In addition, advancements in observational cosmology continue to reveal the universe's vastness and complexity. Telescopes like the James Webb Space Telescope, with its extraordinary sensitivity and resolution, promise to uncover even more hidden mysteries of the universe. Future observations might shed light on the earliest moments of the universe, providing insights into its ultimate fate and the fundamental laws governing its evolution. Beyond observational cosmology, particle physicists are investigating the fundamental particles and forces that shape the universe. The quest to unify gravity with the other three major forces, electromagnetism, strong nuclear force, and weak nuclear force, remains a central goal of theoretical physics. Concepts like quantum gravity and string theory offer potential mechanisms for understanding these fundamental interactions at both the smallest and largest scales of the universe. In the realm of quantum mechanics, the nature of time itself remains a subject of intense debate. Time, as a linear progression from past to future, is challenged by quantum theories that suggest time may be nonlinear or even illusory at a fundamental level. Understanding the nature of time within the context of cosmological models could reshape our view of the universe's origins and evolution. Meanwhile, the search for extraterrestrial life continues to captivate the public imagination and drive scientific inquiry. The discovery of exoplanets, planets orbiting stars outside our solar system, has expanded our understanding of planetary diversity and the potential for habitable conditions elsewhere in the universe. Future missions, such as the James Webb Space Telescope's exploration of exoplanet atmospheres, might provide evidence of biosignatures indicative of life beyond Earth. Notwithstanding these scientific endeavors, social and philosophical reflections on the universe enrich our understanding of our place within it. Questions about the meaning of existence, the possibility of intelligent life elsewhere, and humanity's future in space exploration provoke thought and discussion across disciplines. As we stand on the threshold of a new era in space science and cosmology, energized by technological advancements and theoretical breakthroughs, we are reminded of the vast interconnectedness of everything, from the smallest subatomic particles to the immense cosmic structures spanning billions of light years. The universe reveals its secrets to those willing to explore. Ultimately, the exploration of the universe and the origins of existence is a journey that transcends disciplinary boundaries and challenges our most fundamental assumptions about reality. The discoveries made by instruments like the James Webb Space Telescope offer tantalizing glimpses into the early universe, raising new questions about creation, evolution, and the future. As we continue to unravel the mysteries of dark matter, dark energy, and cosmic evolution, we draw closer to a deeper understanding of the universe and our place within it. Through collaboration among cosmologists, physicists, philosophers, and technologists, we embark on a grand journey to uncover the universe, a quest that promises to reshape our understanding of existence itself. Whether exploring the depths of black holes, grappling with the movements of distant galaxies, or examining the nature of reality, each revelation brings us closer to unraveling the intricate tapestry of the universe. As we venture deeper into space, driven by curiosity and a desire to comprehend the universe's vastness and complexity, we are reminded of Carl Sagan's words, "Somewhere, something incredible is waiting to be known." This sentiment captures the essence of scientific inquiry, a continuous journey of discovery, wonder, and enlightenment that continues to inspire generations of scientists and thinkers alike. In the words of Albert Einstein, "The most beautiful thing we can experience is the mysterious. It is the source of all true art and science." As we confront the mysteries of the universe, we are invited to embrace uncertainty, challenge our assumptions, and seek new perspectives that expand our understanding of the universe and ourselves. Thus, the exploration of the universe is not only a scientific endeavor, but a profound human quest for knowledge and meaning, an odyssey that transcends the boundaries of space and time, inviting us to ponder our place in the grand tapestry of existence. As humanity delves deeper into the mysteries of the cosmos, we are reminded that every discovery reshapes not only our scientific paradigms, but also our philosophical understanding of existence. The sheer enormity of the universe, with its trillions of galaxies, inspires both awe and humility, challenging us to reconsider our significance within this vast expanse. One of the most compelling aspects of modern cosmology is the interplay between observation and theory. Instruments like the James Webb Space Telescope, gravitational wave detectors, and particle accelerators bridge the gap between the observable universe and the theoretical frameworks that seek to explain it. These tools allow scientists to test hypotheses about the nature of spacetime, the behavior of fundamental particles, and the dynamics of cosmic expansion, paving the way for breakthroughs that could redefine our understanding of physics. At the same time, the quest to understand the universe inevitably leads to profound ethical and existential questions. If life is discovered beyond Earth, be it microbial life on distant exoplanets or signals from intelligent civilizations, how would humanity respond? What responsibilities do we bear toward life forms that may share our universe? And how might such discoveries influence our cultural, religious, and philosophical worldviews? In addition to the search for extraterrestrial life, the ongoing exploration of black holes, neutron stars, and other extreme cosmic phenomena continues to shed light on the nature of matter and energy under the most intense conditions. These studies push the boundaries of theoretical physics, offering glimpses into realms where quantum mechanics and general relativity converge. As our understanding deepens, the role of collaboration becomes increasingly vital. The challenges posed by cosmology and astrophysics are too vast and complex for any single discipline or nation to address alone. International partnerships, interdisciplinary research, and open scientific dialogue are essential for tackling the mysteries of the universe. Moreover, the pursuit of knowledge in the cosmos mirrors the introspection required to address challenges here on Earth. Climate change, resource scarcity, and the quest for sustainable development demand the same spirit of innovation, collaboration, and resilience that drives our exploration of space. In seeking to understand the stars, we are also reminded of our shared responsibility to preserve and cherish our home planet. Looking ahead, the next decades promise an era of unprecedented discovery. Upcoming missions, such as the next generation of space telescopes, lunar and Martian exploration, and advancements in artificial intelligence, hold the potential to answer some of the most profound questions about the universe's origins, structure, and fate. As we continue this journey, the universe beckons us to remain curious, humble, and united in our quest for knowledge. The story of the cosmos is not just a scientific narrative, but a testament to the resilience and creativity of the human spirit. In the grand tapestry of existence, every revelation is a thread that connects us to the infinite, reminding us that the pursuit of understanding is as boundless as the universe itself. And so, with each step forward, we reaffirm our commitment to explore, to question, and to dream of what lies beyond.